welcome to Matter Over Mind. My name is Stephen. I'm a business psychologist, and as ever, I've got the physics guy, which is Thomas. Hello, Thomas.
Hello, I'm Thomas, the experimental physicist of the duo.
Cool.
We're going to be talking about the geometry of space this week.
Indeed.
The shape of the universe.
That's right. And the reason we're going to talk about that is because it was asked for, and this comes from Rachel from our Facebook group. So just a shout out to remind people to join the Facebook group and check it out, because I tend to post there quite regularly. I noticed you started to post on there too. So,
yes.
We've got a VIP on there now. Thomas is posting. So, and that's good. I've been out tonight, by the way. We're recording on Tuesday the 25th of February. And I've been out in the garden to see the planets. They're not all lined up in a nice row, but they are all apparently visible in theory in the night sky tonight. It's something that only comes around every now and again. You can see 3 with your naked eye, and I've put photographs of what I've seen on the Facebook group. So if you want to check those out, you can. I mean, obviously they're fairly small. It was just an iPhone that I was using, but it is quite amazing, especially Venus. It's absolutely beautiful. So yeah, that's why you should check out the Facebook group, because we'll remind you of interesting things like that.
Yeah, unfortunately, there's a lot of light pollution here where I live, so it would be a pointless exercise to look at the sky tonight.
It's a shame. So anyway, check out the Facebook group. You can have a look at the pictures. Right. Okay. So yes, Rachel. Then I asked for topics that people would be interested in us talking about, and Rachel said she'd like us to talk about the shape of the universe. She said, "I remember once thinking that maybe it's like a donut, the round one with a hole in it, I suppose, as opposed to a jam donut, which would be really cool. But no, the one with a hole in it." And then I heard that was actually theorized. So yeah, that's really interesting, and we're going to talk about that today. So Thomas, you're prepared to talk about this topic. Where should we start? What is the shape of the universe?
So before we start talking about the shape of the universe, we should probably kind of understand what shape really means, right?
Okay.
By shape, specifically, I'm talking about the geometry of something. So the coordinate structure of something. So
okay.
I'll kind of break this down a little bit. So, for example, an example of a geometry would be a plane. So like literally a piece of paper, for example, that's what's called R2. So it's a 2-dimensional Euclidean plane. So basically it just means if I move left by 1 unit and up by 1 unit, that 1 unit measures the same length. Okay. Basically, so it's regular space. It's how we would pretty much interact with the world most of the time.
Okay.
So another example is S2, which is the surface of a sphere. So the 2 denotes there the number of dimensions.
Yeah.
So obviously a piece of paper is essentially a 2-dimensional plane, right? You can
go up and down.
And Y. Yeah, left to right, and that's it.
Yeah.
So S2 is the surface of a sphere, or sometimes called a 2-sphere. Basically, it's basically what we live on. We live on the Earth, which is a globe, and it has so that's the geometry that we exist on. So that's the general idea, and there are other additional topologies. Additional geometries like toroidal and so on. But the easiest ones to explain are Euclidean, R2. Spherical also is Euclidean, but it's just a different shape. Right. Cool. So that's roughly what geometry is, and it's quite easy to kind of determine what geometry something is when you sort of exist in a higher dimension. So, for example, I gave the case of a piece of paper, a sort of 2-dimensional plane. So we're 3-dimensional beings, or we 3 spatially dimensioned beings. Mm-hmm. So we can kind of look outside of the 2-dimensional plane and say, oh, well, there's up, down, left, right. That's it. Similarly, with a 2-sphere or just spherical surface, because we live in a 3rd dimension, we can pick up the ball, move it around, and we can see, oh, this surface is spherical. So that's quite easy to do, right? But what if you exist now in that geometry? What if you're an ant on that page, or you're a human on the Earth? how can you tell? You can't. It's not so easy to just leave the geometry you exist in to investigate. So that's the sort of idea, or rather, that's how we can even say what shape our universe is, right?
Okay.
Because there are techniques you can use to determine what geometry you exist in, sort of intrinsically, I guess.
Okay, let me just see if I'm understanding that. So if let's imagine, I don't know, there were some creatures, beings who were only two-dimensional, and they lived on literally like a piece of paper, and they only had two dimensions, so they could move forwards and backwards, they could move from side to side, but they couldn't move above the paper or below the paper. So they lived literally in a two-dimensional world. So we can understand that world quite well because we live in three dimensions, so we can look at that world from above or below, and we can understand those two dimensions quite easily, can't we? We can say, oh look, those creatures exist on a two-dimensional plane. They can only go this way and that way. But if we were one of those creatures, it would be kind of difficult to understand what shape that piece of paper was, or whether it was flat, or what it was, because you'd be living in it. And that's the problem we have, because we live in three dimensions spatially. We can't sort of sit outside of those three dimensions and look back and say, I wonder what shape that is, because we're in it. And that's the challenge, isn't it? When it comes, because we live in the universe, and so we can't sit outside the universe and look at it from the outside and say, oh, that's the shape, because we're in it. So I guess that's what you're saying.
Yeah, exactly. It would make life a lot easier if we could, but unfortunately we can't. And of course, the other caveat there is, similar to the little creatures on the plane that you described, we're very small by comparison to the geometry we exist in. So the Earth obviously is a big globe, but locally in our sort of kilometre or so length scale, it's flat basically, right? It's the curvature is negligible on the scales that we sort of engage with day to day. It's only when you go up in a rocket or even a plane that you'll start to have to consider the geometry, which is why plane flight paths sometimes look weird on a flat map, because they're having to navigate a globe, so you have to think about that. But in everyday life, you kind of don't really have to think about the fact that we're not on a flat space, even though we are. So that's the other caveat. Everything is so vastly big in the universe. It just looks flat to us. In the same way, the floor or the railroad tracks for the trains just look like they're on a flat surface. So that's the other caveat. So that's a lot of rambling, but how can we tell? How can we sort of internally decide what geometry we exist in? And the example that if you Google will probably come up, because it's always the example, is looking at a triangle.
I remember that one.
So everyone learns exactly. Everyone learns at school that a triangle has internal angles that sum up to 180 degrees.
I remember that.
So if you draw a triangle on a piece of paper, you add up all the angles, you'll get 180 degrees. Cool. And that makes sense. But now suppose you don't draw a triangle on a flat piece of paper. You draw it on the surface of a ball or a globe or something. Now it turns out, because that surface is convex, so it's sort of outwardly round, if you draw a triangle and put it onto the spherical surface, then all the internal angles are greater than 180 degrees. So they add up to more. And similarly, if you put it on a concave surface, so I guess the inside of the ball, they would add up to less than 180 degrees. So it's a little trick to basically draw a triangle on a surface, add up the angles or work out the area inside the triangle, and then depends whether you get less than, equal to, or greater than 180 degrees, or the area, fiddle factor, whichever method you want to use. That can kind of tell you what geometry you exist in. So if I went in my garden, sprayed a big triangle on the grass, it'd probably tell me 180 degrees. But if I did it on a large enough scale, if I drew a line from Oxford to London to wherever else and so on,
Yeah.
On that scale, it's probably big enough that you'd start to notice. And they never did it countrywide, England to Germany, say, down to, I don't know, Spain or whatever and back.
Yeah.
Then you'd definitely notice.
Yeah.
So that's basically how. That's how you can determine what geometry exists in without having to have access to a higher geometry.
So that's how we do it on the Earth. That's how we knew that the Earth was a sphere before we even sort of went around the whole of the globe. So this geometry was understood many years before we'd explored the whole of the Earth, and indeed before we went up into space.
Yeah, exactly. I mean, geometry is probably one of the oldest subjects, really. I mean, it's, if you think about it, it's
like Euclid. He was a Greek philosopher, wasn't he? And Pythagoras, which we all remember from school. I mean, he was another one of those Greek philosophers and mathematicians.
Yeah. So I mean, this is an ancient subject, really, and it kind of makes sense, right? You kind of, if you break down maths at its most basic, shapes are fairly straightforward, right? So understanding how shapes work together, has proven to be quite useful for us, really.
Yeah.
So that's good. But yeah, so that's how you'd kind of do it. You'd find, and of course I've explained examples in 2 dimensions just because it's easy, but in principle the similar principles apply when you increase the dimension. So there's likely an equivalent method if you're in a 3-dimensional space, how you would determine the flatness or sphericalness, if you will, in that geometry. It may not exactly be with the triangle method, but it would be something similar to that, because it's quite an easy test. Cool. So that's geometry covered. We can tick that off our list.
Done.
So it turns out some physicists and astronomers and such have done this test looking at the CMB, the cosmic microwave background. So what the CMB is, for those who don't know, it's the oldest light we can observe in the universe. You look out into space and put long exposure time on your telescope, you start to see this sort of background appearing. And this basically is, after the Big Bang, there was a few epochs happened, but because of how light traverses through material, in the really early stages of the universe, the sort of plasma that was there was too hot and opaque for the light to sort of penetrate. So as it kind of expanded and cooled, then the plasma became essentially transparent to these rays, and that's the first light we saw. At the instant when the plasma became transparent, to the light being emitted.
Right.
That's what we can see.
So this is I'll put a picture of this onto the Facebook group. One of the things that unfortunately is quite apparent when you start looking at this is that it's easier for the YouTube boys and girls who can use pictures, because we're talking about a shape, and obviously shapes are much easier to illustrate on video or photographs and stuff. But I'll put that picture of the background radiation on. It's fascinating. And am I right in saying that this is like under 400,000 years into the start of the universe? It's like that is like nothing really. It's
really young.
That's amazing.
It's kind of crazy. If you look at there's this. I'll send you the picture actually to put on or maybe I'll put it on the Facebook group. But there's the classic one that you learn, and so we've got. I'll just sort of quote it here. So we've got. So you've got the Big Bang happens, and then you get something called nucleosynthesis at 0.1 seconds to 1,000 seconds after the Big Bang. So that's basically it cools down enough for the nuclei of atoms to form. Before that, it was too hot for the quarks to kind of stay bound. So then at 0.1 seconds after the Big Bang, they started to, I guess, recombine, or not recombine, just begin to combine to make atoms. And then, so here we go. Universe becomes transparent 380,000 years after the Big Bang. So 380,000 years compared to 13.8 billion years, which is how old it is like you say, incredibly young.
That is like baby universe, and we can see it. We've got a picture of it. It's just amazing.
It's cool.
It's amazing.
It's almost mind-boggling. It almost doesn't. It feels like sci-fi, but because of as we all know now how light works. That's how we know how old it is.
Cool.
But so basically, I'm not particularly sure on the explicit details on how this was done, but there are structures that you can make out from this CMB.
Okay.
And then basically by doing either the triangle trick or something similar, you can estimate the geometry of the universe. Cool. And it turns out it's mostly flat. According to the CMB, there's a good argument to say it's mostly flat, plus minus some error. But
okay. And so when we say it's flat, what does that mean? Because I think a lot of us would think, oh, that we're back to our plane again, we're back to our piece of paper again. But that's not really what we're saying, is it?
No. So it's tricky without using the kind of the jargon, but basically, so flat, or I guess, I mentioned before R2 is just the I guess the symbol or name given to a flat plane. So R1 would be a straight line. So a one-dimensional flat geometry is just a regular line.
Yeah.
Two-dimensional flat is a plane. Now this is assuming infinitely spanning, basically.
Yeah.
And then I guess what's more than a plane? I guess a cube, I suppose, but it's not. It's the volume of the cube, not the surface. Sure. So it kind of becomes a bit more abstract when you start to think of, we can in the same way you look at a ball, you think that you're seeing a 3D object, but you're not really. You're seeing the surface of a sphere. You can't as a three-dimensional being see the volume. You just see the surface, and because we have brains and perception, we can understand it's spherical. But basically, in the same way, so imagine on a piece of paper now, you draw a circle. So that's a two-dimensional shape, right?
Yeah.
A circle. We're in 3D, so we're one dimension above, so we can see the circle. Suppose now there's a stick person on the piece of paper. So they're a two-dimensional being. Yeah. The circle is also two-dimensional, but what they would observe is a straight line.
Yeah.
But because they can move around in the 2D space, they could probably determine that the circle is also two-dimensional.
Right.
Because otherwise it'd just be a dot if it was a line, right? So the dimension that you exist in, you can't perceive that same dimension.
Yeah.
Spatially, of course. So in the same way, the stick person can't actually see the full circle. They'd have to move around in their 2D space to know it's a circle. We can't see the third dimension of a sphere. We see the surface of a sphere and we can move around, so we know it's three-dimensional. So that's why it's kind of hard to explain what flatness means in 3 dimensions, because we're living in it.
Yeah, that makes sense to me. Cool.
Yeah. Okay. Cool. But yeah, so it turns out the CMB indicates that we live in a mostly flat universe.
Okay.
Cool. Okay. So we're going to take a little bit of a change of pace now and start talking about the cosmic expansion. It all links back to the same stuff, but for now it's a bit of a tangent.
Yeah, because I suppose that's logical, because you can't really talk about the shape of the universe without thinking about kind of how it got there, and I suppose that's why we now need to talk about the expansion of the universe. Yeah. Yeah,
exactly. Also, it's an evolving thing, right? It's currently expanding. So who's to say in a billion years' time it's still flat? It might have changed, right?
Good point.
And we'll get to that at the end. But yeah, so basically, we need to know how it got here.
Okay.
So it is expanding, and it's expanding at an accelerated rate, which is, I guess, I think it's cool. It might be terrifying. Who knows?
Just explain to me what that means. It's expanding at an accelerating rate.
Okay, so if you look at the classical mechanics, if you look at Newton's laws, if a force is acting on something, it accelerates. So its speed is going up, basically. So if you're at constant speed, if you're traveling along at 70 miles per hour in your car, you're not increasing speed or decreasing. You're said to be at constant speed, right? You're just moving at a constant speed. If you're accelerating, it means there's a driving force somewhere. And accelerating can either mean you're slowing down, so your velocity is decreasing continuously, or speeding up, so your velocity is increasing continuously. So an acceleration basically means there is a change in velocity. That's the definition of what acceleration is.
Okay.
So if the universe was expanding, fine. It would be like, you blow up a balloon. But now imagine if you blow up a balloon, but it wasn't a sort of a constant force in your breath. You were, as time was going on, you're putting more and more. The rate at which you're blowing out air was more and more, so the balloon would, it would expand, but quicker than it were if you were keeping constant. So basically, yeah. So the rate at which the universe is expanding is speeding up. So that's what that means.
Okay. Yeah. So it's running away from us quicker than it did a billion years ago.
Yeah, exactly. Yeah.
Okay.
So if you imagine it like a curve, you've got velocity on your y-axis and you've got time on your x-axis. It's not a straight line. It's a curve upwards.
Okay.
Basically.
Okay.
Cool.
Okay.
Well, how do we know that? So it turns out by looking at these things called standard candles, which you've probably heard of, you can see basically. So imagine you had a light source and you knew how bright that light source was.
Mm-hmm.
If I move it away from you, it's going to get dimmer, right?
Yeah.
So basically, and light travels at a constant speed. That's known. It's always the same speed as we discussed way back in episode 1. Yeah. So if you know how bright your light source is, and you know how fast it's moving, because the speed of light is fixed, then you can work out basically how far it is and how quick it is. Basically, speed is distance over how long it took you to travel that distance. So you can basically, with those 3 variables, you can work out, and the brightness, you know how fast light travels, you can work out the other variables. And it turns out, if you look at this, you look at different standard candles at different distances away, they're red shifting. So basically the light is, how much the light stretches tells you how fast they're moving, and it indicates that they're moving far away from us at an accelerated rate. Cool. So what is a standard candle? How is it that in the universe there's this convenient light source that we know and is constant? So standard candles are basically, as I said before, they're a light source with known brightness, known absolute brightness. And the standard candle we use is something called a Type 1a supernova. So if you Google standard candles, that's the first thing that will show up, Type 1a supernova. So a supernova generally is what happens when a star comes to at the end of its life cycle. It kind of implodes in on itself, reignites in a big explosion. But Type 1a supernova specifically is that explosion when you have a binary system of I think it's a white dwarf, so a very extremely hyperdense star and a second star. So when those guys collapse in on each other and they explode, that's the Type 1a supernova.
Okay.
So imagine you blow something up. There will be a ramp up as the explosion gets hot. There'll be a peak brightness of that, and then it'll die off, right?
Yeah.
So it'll get brighter and brighter and brighter. It'll get to a maximum brightness, and then it'll slowly decrease again. Right.
Yeah.
So again, the specific mechanics, I'm not a stellar physicist, so I wouldn't know the specific details. But basically, there are certain materials in white dwarfs that give rise to how much or what kind of light it's giving off. And the white dwarf is way heavier than the second star generally, because white dwarfs are extremely heavy. So when it collapses, due to the elements contained in the star, it's going to have a characteristic, basically, light curve, as it's called. And the peak of that light curve tends to be roughly the same luminosity or the same brightness, regardless of which supernova it is. In the same way, like spectral signatures are the same. So you remember how anytime I talk about quantum mechanics, I talk about the shelves.
Yeah.
The gap between the shelves for hydrogen, for every hydrogen, the gap between the shelves are the same. So if you see light emitted between shelf 1 and shelf 2 on a hydrogen atom, it's the same for all hydrogen atoms, basically. Each particle is identical in that sense. It's the same is true of this brightness. Each Type 1a supernova gives basically the same light curve. Okay. So it's a good indicator.
So that's just brilliant. So that means that we've got this kind of constant standard. We've got this standard in the universe that we can look to and say, right, that gives off the same amount of light as every other instance of a Type 1 Type 1a, is it?
Yeah, type 1a, yeah.
Type 1a supernova. So every time a type 1a supernova is spotted, it essentially gives off the same amount of light.
Yeah.
So here, there, everywhere, same amount of light. So that is a standard that we can use. So if it's closer, we know how close it is. If it's further away, we know how far away it is. And you also said that because of the fact that the universe is expanding, this helps us to understand how quickly the universe is expanding. And you said that's because of the redshift. So you need to explain really what the redshift is to us, so that we can understand how that tells us the rate of expansion.
Yeah, so, okay, so, because it's a standard, if it's closer to us, it'll appear brighter. If it's far away from us, it'll appear dimmer. Okay, cool.
Yep.
So that's assuming a universe that's kind of static, right?
Yeah.
If you're in a room that isn't moving and I move a light source closer or far away, it'll dim or brighten. Because we know that the brightness is constant, how dim it is tells us how far away it is. Cool.
Yep.
So there's another thing there. So its brightness is essentially the same, but the light curve, the signature of that brightness is also the same. And it turns out when you're moving through space, so light is one model of light is it's a wave. So when you have waves or something with a periodic form, when you travel into close to them or away from them, that will distort the wave in your frame of reference. So you've probably heard sirens drive past you, like a fire engine or a police car or something. As they come towards you, they appear high pitched, and then as they drive away from you, they appear lower pitch.
So this is the famous na 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 that you hear, and this is because these are sound waves, and as the object moves closer, the sound waves get shorter, so it sounds to us like it's higher pitch. And as they move away, the sound waves get longer, so it sounds to us like it's a lower pitch.
Yeah, exactly. Yeah.
And this, when Celine was growing up, she'll tell you this, that this was my sad dad fact. I would also always say, oh, did you hear that? The ice cream van doing that, because you can hear it with an ice cream van as well. That's called the Doppler effect. Because I learned that in my Physics for You book that I've told you about. It's in there. The Doppler effect is in there. So, but the interesting thing is that same Doppler effect is visible with light, so we can see the difference in objects that are coming towards us and going away from us. And so, if it's going away, it looks more red. If it's coming towards us, it looks more violet, isn't it? Ultraviolet.
Yeah.
So or blue, I suppose. So when you talk about the redshift, this is the fact that we can see it's going away, but in the difference between that redness, you can tell how fast it's moving away. Yeah.
Yeah, exactly. And sort of, I mean, why I sort of emphasize the profile of the light curve, the signature of the light, is because if I have a shape and I stretch it, so I redshift it in this analogy, and then I stop stretching it, and then I look at that picture, it looks different to the unstretched shape, but if you went on Photoshop or something, you could compress it, and it's the same picture.
Right.
The redshift or blue shift, for that matter, doesn't alter the properties of the picture. It just stretches it, or in this case, the light. It doesn't change the signature of the light or the signature of the frequency. Of the signal. It just stretches it or compresses it. That's all it does. So that's why, even if it does get redshifted, you can still work out what it would look like if it wasn't redshifted or blue shifted. And that's just because, like I say, if you imagine you've got a wiggle and I stretch the wiggle, it's the same wiggle. It's just been pulled apart.
Squeeze it back again. Yeah,
exactly. So by looking at a bunch of type 1a supernova. And again, there's another reason you can kind of tell them. I sort of mentioned this light curve, and maybe that wasn't too clear, but you can, by putting light through a prism, you get the rainbow. You've seen that, right?
Yeah.
So actually, if you look at, I guess, with a microscope at that rainbow, there'll be bands of wavelengths that are missing, and that's because in our case, if you put the sun's light through a prism, there'll be a few lines missing, and that's because there are elements in the sun that absorb those specific wavelengths of light because of quantum effects. So by looking at the rainbow made when you put the sun's light through a prism and searching for the wavelengths that are missing, you can work out what materials make up the sun, and that's kind of how we know what stars are, or what most stuff in the universe is made of.
Okay.
So that's another way.
Wow.
You look at the light given off by a type 1a supernova, you kind of find the characteristic, fingerprints, if you will, and then that's why you can stretch it or compress it, and you still know it's an event of that type, and this type specifically is the type 1a supernova. So just a caveat there to potentially answer some questions that people may be thinking.
Okay.
But yeah, so it turns out, looking at the Doppler shifted signals from a bunch of type 1a supernovas, it turns out, the universe is expanding at an accelerated rate, and due to the CMB structures, it's also flat, or mostly flat. Cool. Okay. So we've got two pieces of the puzzle. So I mentioned before also, if something's accelerating, there must be a driving force. If there's no force, you're at constant speed or at rest. So that's Newton's first law. If you're at constant speed or at rest, if there's no force acting. If there is a force acting, you're now accelerating. The thing's accelerating. Yep. So that's the idea behind dark energy. There's kind of two dark terms, if you will. There's dark matter and dark energy. Dark matter is a different thing, nothing to do with dark energy, so I won't talk about that here. But dark energy is just the kind of general, broad term for the thing that is accelerating the expansion.
So we think that somehow dark energy is sort of pushing, and I use that term in a very layman's way, but pushing the universe apart. It's making it go faster. And that's one of the reasons we think there is dark energy, because that was a surprise, right? That's only this last sort of, I don't know, few decades that we spotted this, because we assumed the universe would sort of gradually slow down with all the weight of the gravity of all the objects in it. But we found that it was speeding up, which meant that we needed this other thing, which is dark energy. Is that right?
Yeah, pretty much. Yeah, so it all kind of comes back to, again, this sort of energy balance, as it always does in physics. You got to keep you got to do your accounting properly. So so they discovered, okay, it's mostly flat. Okay, cool. They discovered also it's accelerating. But if there's no dark energy term, the energy balance is such that it's just going to collapse in on itself, and again, game over, I suppose.
Eventually, we'd come to the big crunch. That's what they thought might happen. It all starts coming back together again. But we don't think that's happening now, because that's not what the observations say.
So what's interesting about that actually is that might still be a possibility. The big crunch or the big chill, which is the case where it just expands indefinitely, or it might come to the point where it just expands to a point and then just equilibrates and stops. So the expansion definitely is happening, because we can see it from the redshifted standard candles. It's mostly flat from the CMB. And we know also what's in it. We can see the stars and the galaxies and stuff, and you can estimate how much matter or material there is. So you've got these three things. So you've got the mass energy, the mass density. You've got the curvature density. I'm using density probably incorrectly here, but you've got the mass stuff, the curvature stuff, and the expansion stuff. When all those things add together to make one, we're all happy. And independently, those things can be confirmed. So kind of interestingly, that kind of concludes really the shape of the universe bit. But that's at the moment. Right now, as it stands, we are, at least in the observable universe, mostly flat, and we're accelerating and so on and so on. That's not to say at some point that will remain to be the case. So, for example, as we continue to expand, this energy balance may become shifted in one way. It may be matter dominated, or it may be curvature dominated, or acceleration dominated. Who knows? But to keep this sort of equation equaling one of those terms has to give. If it continues to accelerate, then one term's going to get bigger, so one needs to get smaller. So to account for that, the curvature could be the term that buckles, right? You could get the case where you have, instead of flat, now it becomes either, negatively curved or positively curved. I won't particularly explain what that means in real terms, but basically, it could become convex or concave. So imagine you've got like a saddle, you've got the surface of a ball, and then you've just got flat. It's kind of hard because I've been discussing geometry, whereas when you look at this curvature, it's the curvature that they're looking at, not the geometry. So that it's subtly distinct, but they're not quite the same thing.
So this is topology, isn't it? Really, this is the sort of big picture of the universe, rather than measuring angles and shapes.
Yeah, exactly. So an example of what that might mean. So a topology is a geometry that is transformed by stretching or whatever, but has the same, I guess, properties. So, like for example, you have a donut, which is a closed surface with a hole in it, and then you look at a mug with a handle. Well, if you can in principle deform. Imagine that the mug is like a stretchy fabric or whatever. I can in principle stretch the mug such that it is just a closed surface with a hole in it. The handle is the only hole in a mug, right? The bit that you put your drink in is just a flat surface that's been deformed. Okay. Whereas so a donut and a mug have the same topology. That they're a closed surface just with a hole in it. And for example, a pair of trousers, that you've got the 2 feet hole and then the bit where your waist goes in. So that there's no way you could deform an infinitely stretchy pair of trousers such that it only has 1 hole in it now. There's always going to be 3 bits, or I guess 2 holes in it.
Yeah. So you'd have to. So an object with, I can't think of a knuckle duster, maybe, which has got 3 holes in it, is the same topology as a pair of trousers.
I don't think it is actually, because
the pair of trousers, the waist hole connects to the other 2, doesn't it?
Yeah. So it's, I guess, you
have to think of something else.
Shape. Yeah. So I guess, like your socks is the same as a piece of paper as far as topology is concerned. Right,
that's a better one. Yeah, I don't know how I thought about knuckle dusters. That's really odd. I've never ever used a knuckle duster ever. Okay, great. So topology is something different, really, to shapes, which I suppose. Just to confirm that. So, the topology of a pair of socks or a sock is the same as the topology of a sheet of paper. Although to you and me, we might think they're completely different shapes. In terms of topology, they are the same. Yeah, so when we talk about
a bowl is the same as paper or a plate or something.
Right. Yeah. And that's because it's got one surface area essentially, and so there's an inside and outside, an up and a down, same as socks, same as a sheet of paper, same as a bowl. So they would be the same topology. So if we're trying to describe the universe as a shape, we what we're really talking about is its topology. So the universe, if we said the universe is the shape of a bowl, we might as well be saying it's the shape of a sock. Yeah.
Or it's a cube or something.
Yeah. If we're saying that the universe might be a torus or a donut, which is what Rachel suggested, then it could be, but in a way we wouldn't think about it in terms of like we would think about a donut, but because the topology of it means that in reality, if we were this being who could sit outside of the universe and look at it, we wouldn't necessarily see the shape of a donut. It could have any shape that had the same topology. It could be the shape of a mug. Yeah. Because that would be the same.
Yeah, exactly. So
that's really interesting and weird.
Yeah. So it's a bit strange, but I guess in the same way, you know, when you scale up to the grandiose scale that is cosmology,
Yeah.
it all kind of just becomes a bit abstract. Really, we can't really
Mm.
engage with something that's that big. So yeah, it's you know, yeah, a mug being the same as a donut. Yeah, I mean you can kind of see it. But yeah, if we have this basically fabric that's expanding, it's going to kind of get warped over itself, or it could potentially kind of warp over itself or stretch in funny ways. And as long as it's, well, there's a chance it could tear. I don't really know what that may be, but yeah. So what was
Okay.
so yeah? So the point there is the universe is expanding. It's locally flat, and yeah, the fact that it's flat now doesn't necessarily mean it'll stay flat forever, and that's flat in a I guess topological sense. It has no curvature, I guess.
Yeah.
Yeah. So what was interesting though is I was reading a little paper to prepare for this episode, and they were talking about the I guess the topology of the universe. And this one paper, I'll search it out to find actually what institution did this research, because I'm forgetting at the moment. But they gave an example that it could be R cross T2, right? So if you recall from earlier, R means Euclidean flat.
Yep.
So obviously it's it's three spatially dimensional. So there's R cross T2. So S2 or R2. R2 was like a plane, like a piece of paper. S2 was a surface of a sphere. T2 is a surface of a torus or a donut.
Oh.
Very interestingly. So this person sort of says that there's no reason why the geometry of the universe isn't governed by flat in 1 and toroidal in 2 dimensions. Now what that actually means I have no idea, because this is the realm of
So flat in 1 dimension and a torus in 2 dimensions. Is that what you said?
Yeah, that's what this guy's proposing. Like I say, what that actually means, I can't picture one dimension with one geometry and then the other two being in a different one. The alternate he said was it maybe is R2 S1, so 2 spatially flat, 1 spherical. Again, I don't have the geometric background to appreciate what that actually means, but I thought it was interesting to give some credit to that Facebook comment that maybe it is donut shaped. Who knows?
Yeah. Well, I mean, I've seen quite a few pictures of donut shaped universes. I don't know why that is. I think it is quite. It makes a good picture, doesn't it? So
yeah.
It's kind of, it looks quite cool when you see that, and again, by the sound of it, by what you're saying, there's no reason why it couldn't be.
Yeah.
That, but we just don't know, do we?
No, and I guess an interesting point about donuts or toruses, as they're, I guess, more rigorously known. So when I was doing some reading, again, I don't fully get this, but they're talking about the idea of a flat torus. So this being the properties of the space have the same properties of a torus without it actually being donut shape. So I'll kind of explain what that means. So imagine, you know that scene in The Matrix, I think the second movie, when he's in the train station.
Yeah.
Neo. Yeah. And the train man tells him he's stuck in this place. He kind of has to follow his rules. So he runs down the train tracks in one direction and appears on the other side, running back into the station.
Yeah.
Right. So that's what's called a periodic boundary condition. So the boundary of the train station kind of loops back on itself.
Yeah.
So imagine you're on the surface of a cylinder, and you walk in the
around it.
Yeah, you walk around it. You're going to end up at the same spot you were in, right?
Yeah.
Now imagine you close up that cylinder. You've got a donut. So now if you walk along the length direction, then you'll end up where you are. So if you flatten out a torus into a piece of paper, if you walk upwards far enough, you'll leave the top end of the paper, and then you'll come back in the bottom of the paper. Similarly, if you go left all the way, you'll leave the left side of the paper and appear on the right side of the paper. Yeah. So that's your space kind of containing the properties of a torus without actually being in a donut. So, yeah, I thought that was just an interesting aside to bring up.
Yeah, that is interesting. I saw something like that on a video. I should mention a couple of videos I watched actually before we started this. There's a video called Up an Atom, which is a bit of a pants name, but Jade, she does it, and she's great actually. She's really good at it. So she talked about that, and I think she described that as kind of like I suppose, a mathematical way of explaining it and then predicting what sorts of things can happen, because it is very difficult to sort of understand what would happen with a torus. I also watched a YouTube video by Joe Scott, and his question was, is the universe a Pringle shape? So that's your concave shape universe, isn't it, that you mentioned before?
Yeah, I mean, the Pringle actually has an interesting property of the middle of the Pringle. It's what's called a saddle point, because if you look at the Pringle, it's kind of like a saddle that you may put on a horse. It's got a U-shaped bit, and then it's got like an N-shaped bit, and the middle of the Pringle is uniquely in the middle of the maxima of the N and the minima of the M. So it's a saddle point, and it's interesting because mathematically the way you determine, I guess, points of equilibria on a curve. There's an extra step if you're in a saddle point that you need to take. Normally, if you're in like a bowl, you can be like, okay, it's in equilibrium when it's at the bottom of the bowl, when it's at that minimum, the point of zero gradient. When it's on a saddle point, there's an extra step. So it comes up a lot in maths because it's an interesting shape. But yeah, again, in principle, that would have curvature. So it could be that we exist in that geometry.
But we don't think so because, as you said, the evidence from the microwave background radiation suggests that the universe is pretty flat. So I guess we think that's the best model that fits what we currently see. So we don't think it's a Pringle. We think it's flat, but that doesn't rule out a torus or something like that, because that is effectively flat. Although we don't think of a donut as being flat, it is from a topological perspective.
Yeah, well, in the case specifically of R cross T2, it's basic. I imagine this means a two-dimensional flat torus. So the example I gave with the paper, where wall copper come beneath it and so on. So yeah, it's flat in the context, in the sense that it has no curvature, which may seem like the same thing, but there's a nuance to that. But yeah.
Okay. Cool. So you said you had one or two things you wanted to get through. Have you covered the things, and then there was something at the end that you said was a bit of a surprise.
So that was the bit. I mean, the exciting bit was that this theorist was like R cross T2, so potential toroidal universe. That was the exciting little bit of that little Easter egg, just to little nugget that. According to this geometry person, maybe if you think about toruses in completely different ways to how you would actually think about a torus.
Okay. Cool. So, I mean, I think what I've got out of this is that it's very difficult to imagine with our teeny weeny brains the shape of the universe or the topology of the universe. And in a way, that's not surprising, because we are teeny weeny creatures on a teeny weeny ball of rock. As Douglas Adams said, in an unfashionable end of the Milky Way galaxy, it's like, and that is just a small bit of the universe. It's just, again, unbelievably big. You just won't believe how unbelievably big it is,
Yeah.
So,
I mean, we're definitely punching above our weight, I think.
We are, aren't we? And the fact that we can actually do things like take a picture or have a picture of the universe at 380,000 years old. Is it? No, 380 million, is it?
380,000.
380,000. I still can't get my head around that. 380,000 years, after the Big Bang. That's as soon as light is sort of becoming visible because all the clouds or the plasma sort of cleared, and we can see that by using our instruments. That's just amazing, isn't it? That's just amazing.
I mean, it's a almost 13.4 billion year old bang, and we can see that,
and we can see it that earlier than 500,000 years. So that's amazing. We're doing pretty well, but just trying to get our head around the shape of the universe is probably a bit beyond us, but I think we've learned some stuff today. So Rachel, I'm not sure that we've been able to give you a kind of definitive answer on that. I blame Thomas, but I think we've made a good fist of it, and I think the reality is it's still one of those questions that we're still trying to discover, and it's the field of cosmology really that is doing that sort of work. So it's not really your field, Thomas. So I do appreciate you researching that for us today. But fascinating stuff.
Yeah, no, it's cool. I mean, the fact, like you said, the fact that we can even begin to start asking these questions and get some results is pretty wild. But I mean, I suppose the takeaway is the universe isn't a static thing; it is evolving. So the shape now isn't the shape forever. Well, it may be, but isn't necessarily the shape forever.
Fantastic. Well, thank you very much. I really enjoyed that. Very interesting stuff. Thank you. Fascinating. Right. Okay. That's it for today. Don't forget to share the podcast with other people. Just send them a text message or share it on Facebook or whatever social media you use. Let people know about it. So, that being said, thank you very much.
Thank you for listening.
Bye. Bye.